So, again, these are what I'm like just reviewing what Algebra 1 looked like, what solutions could be with two lines. So talk to me about quadratics. What could happen if I had one quadratic and one line on a graph? What could happen? They could have two solutions. So they could have a parabola, and then you could have a line that goes through it like this, and they would intersect twice at these 2 points, and they would have two solutions. What else could happen? One solution. How could it have one solution? Okay, so if the line was on the vertex, which direction? Ooh, I heard horizontal and I heard vertical. It could be both. So if I had a line that was horizontal, it would touch the graph once and it would have one solution. Or I could have, again, a quadratic with a line of symmetry through it that goes through the vertex. It would also touch it once. It would also have one solution. There's a third way that we can have one solution, and this is going way back to your geometry days that were so long ago. If I have a parabola, I can have a line that touches that parabola one time. And that line is called a tangent line. You learned about tangent lines when you talked about circles in geometry. There was tangent lines and secant lines and chords, and yes, you did learn these words.
Not Coach Carson.
Okay, yes, you did learn these words in geometry. So a tangent line, what it does is it comes up on a curve and it touches it and then just immediately comes back off the graph. So it only touches it one time. These are harder to tell for sure that there's only one point there, but there is only one point because that line is tangent. So again, we could have one solution this way. So we've talked about that quadratics and a quadratic and a linear system can have one solution. It could have two solutions. What else could it have? How would it have no solutions? Yeah, if it didn't touch it. So if you had a parabola and then you had a line that was, let's say, down here, then it would have no solutions. Okay. In a system of, so back to our linear system, we said it could have one solution, no solution, or infinite solutions. Is it possible for a system with a quadratic and a line to have infinite solutions? No, because the only way it had infinite solutions would have to be true about those two lines. They had to be the same. They would have to be the same. They'd have to be both parabolas. They have to be the same parabola or the same quadratic in order for that to be true. But we're not talking about the system of two quadratics. We're talking about the system of one quadratic and one line. So if you will look at your 5.2 homework, or your 5.2 notes, we are on page 255. Part B at the bottom says to sketch three graphs of a line and a parabola, one in which they intersect at one point, one in which they intersect in 2 points, and one in which they do not intersect. So that's what I would like for you to do on your three graphs down here. So your graph should look something like this. Again, they don't have to be exactly like this because there is multiple options. But one solution means they intersect one time. Two solutions means they intersect twice. And no solutions means they don't intersect at all. So question for you. All right, so looking at the next page, if I want to solve a system graphically, then all I have to do is graph it and look for what? What am I trying to find? The intersections. So if you look at this graph, it's on the next page, problem A. Where do they intersect? I have a line and I have a quadratic. Where do they intersect? Where are those two places? Approximate. Okay, so look at the blue one. Let's start there. What do you think that x value is there? Maybe positive 0.25, positive 0.5. So pay attention to your scale. If this is 0 and this is 4, what's this middle line here? This is 2. So if this is 2, we're trying to approximate where this is. I'd say probably about 0.5-ish. Approximations are just that. They're approximations. They're not going to be 100% accurate unless you want to do the math, which I haven't at this point taught you how to do the math yet. But it's easy. You'll figure it out. So I have 0.5 for my x value. What would be my y value at that point? -1 or -2? -2. Scales matters. Pay attention to those. Okay, it's okay. What about the green point? Where is that at? What's that solution? Okay, negative 1.75 and then about negative 6, negative 5.5, something like that. So again, I'm okay with approximations here. If you put negative 6, that is fine because that's close. What would be a very wrong answer to this would be negative 4 or negative 4.1 for that y value at that point. So we're just, again, approximating. All right, now we're going to look at, I'm going to skip B for now because I don't like B as an example. So look at the next page, and let's do problem 3 together. I have y equals 3x equals 0. Y plus 3x equals 0 and y minus 6 equals negative 3x. If we're going to solve these graphically, what do I have to do before I can graph them? I have to solve for y. I have to get y into y equals. So how do I do that for that first equation? Minus 3x. So that first one is y equals negative 3x. And what do I do for the second one? I'm going to add 6 to both sides. Can I combine that 3x squared and that plus 6? No, just making sure we understand that. So my two equations would be y equals negative 3x and y equals negative 3x squared plus 6. So I'm going to show you how to do these in your calculator, in your yellow calculator, because you need to know how to do that. Desmos is going to be a lot easier to use for this, but I need you to know how to find it in here so that you have both of them available to you. So we're going to go to y equals. Oops. Okay. So we're going to go to y equals here, and we're going to type in our two equations, which were y equals negative 3x and negative 3x squared plus 6. So we're typing both of those in, and then we're going to go look at our graph. Once you get them both typed in, you're going to go look at your graph, because we are looking for where these two intersect, which we can only find intersections if we're looking at a graph. I'm going to go ahead and zoom 6 so I can get back to my standard window here. So looking at this graph, how many intersections does it have? 2. We can see that. We can see that there is one here in the quadrant 3, and we can see there's one down here, quadrant 2, and we can see there's one down here in quadrant 4. So do y'all remember what buttons you press on your calculator to find your intersection? Second trace, and then number 5. And when you get back to the main screen, you hit enter, enter, enter until you see the word intersection. So the reason I want to go over this with you is not that I don't believe you can press buttons. I know you can do that. I believe that. I believe in you, that you can do this. The problem is, so my first intersection, by the way, is negative 1, 3. If I continue to press second trace 5, enter, 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 it's going to continue to find the same point over and over again. Your calculator needs a little bit of guidance. So it's automatically going to default to whichever point it is pointing at. So look at where the cursor is right now. You can see the cursor is right here on this point. It's going to keep finding that point for you, because that's where it thinks you want. But we don't need that point anymore because we found this answer. Now we need this point, so we need to move the cursor on our calculator. You can see that it's blinking. I need to move it over here. To do that, you either move left or right. Well, which way do I need to move? Right. To the right. So I'm going to move to the right until I get close to the other point that I want, which is down here. I don't have to be exact, but I need to be in that general area, because what I'm doing is I'm now telling the calculator, hey, I don't want this point that was up here at the top. I now want you to find this point for me. It needs you to kind of specify that. Otherwise, it's just going to keep doing the same thing over and over and over again. So now I can press my enter, 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 and it's going to give me my second answer, which is 2, negative 6. So our two solutions were, what was the first one? Negative 1, 3. And, okay. So now you're going to graph this. Now, do you think I'm looking for a 100% accurate graph? No, I'm not 100%. I don't need to be perfect. I don't demand perfection most days. So, but I do know that they intersect at negative 1, 3. So your graphs better intersect at negative 1, 3. That should for sure be a point on your graph. You also know that they intersect at 2, -6. That should also be a point on your graph. Well, that's easy enough to draw your line, because in order to draw a line, you need how many points? 2. So as long as you have 2 points, you can draw your line. And then your parabola, you know it should be negative, so it should look something like this. Again, it's not going to be 100% perfect. I'm not looking for that. But it does need to be somewhat close to what it should look like. Okay? And I'm perfectly fine with you sketching it. You don't need to go to the table and get all the points and plot it. I'm not going to make you do that. Okay, I want to go back and look at the problem on the previous page with you now. All right, so I want to look at question B with you. So it says 3x plus y equals 4.5 and y equals 1/2 times x minus 3 squared. So what's the first thing I need to do with that first equation? I need to get rid of the 3x. So I'm going to minus 3x over here. I'm kind of lazy when it comes to solving for y. I just move stuff around. I don't like do the minus on both sides because I think it's a waste of time. So we just move on. So I have y equals 4.5 minus 3x and y equals 1/2 times x minus 3 squared. And now we are going to graph this. So go ahead and go to y equals, and we're going to type both of these in. So I'm back in y equals. Oops. And I'm typing in both of my equations. So my first one was 4.5 minus 3x. And my second one was 1/2 times x minus 3 squared. So looking at these two graphs, how many solutions do you think it has? One. It looks like this line just comes up and touches the graph. What did we call that earlier? Tangent. So it looks like this line is just tangent to the graph. So we are only going to find one solution. So second trace 5, enter, 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 and it tells me that my intersection, my solution, is the ordered pair 0 and 4.5.